In the last video, we explored some topics related to the stereochemistry of monosaccharides, where we learned to compare the structures of two different monosaccharides to establish whether they were related as constitutional isomers, enantiomers, or diastereomers. Here we're going to go further with that by working through some problems in monosaccharide stereochemistry. Let's go ahead and get started and take a look at this example problem. Taking a look at this example problem, we ask, how are D-glucose and D-mannose related? I've drawn the structures of each of these below as its Fisher projection. Keep in mind, for purposes of this class at least, that you don't need to memorize any of these monosaccharide structures. If you're faced with a problem on an exam that deals with one of these, I would give you the structure and ask you to do a manipulation of it of some sort, or in this case, ask you how these two structures are related. Are they constitutional isomers, diastereomers, or enantiomers? As a reminder, when we talk about constitutional isomers, we're referring to molecules that have different branches, different chain length, or a difference in functional group, such as a ketone versus an aldehyde. For them to be constitutional isomers, they still have to have the same molecular formula, meaning the same number and type of atom, but they have a difference in the constitution, in the structure of the molecule in terms of how the atoms are bonded together. In the case of diastereomers and enantiomers, those are representatives of stereoisomers, molecules that differ only in their three-dimensional shape. Diastereomers have inverted one or more stereocenters, but not all of them. And when I say stereocenter here, I'm using that synonymously in this case with chiral centers. So they've inverted one or more chiral centers, but not all of them. In other words, they are not mirror image stereoisomers. On the other hand, enantiomers refer to situations where all of the chiral centers have inverted. As a result, the structures are non-superimposable mirror images of one another. We can recognize that chiral centers have inverted in Fisher projections because the OH group that was on the right will become on the left for the corresponding position of the other structure. So in the case of D-glucose versus D-mannose, taking a look at this, we initially evaluate for whether the two structures are constitutional isomers by going down the chain and asking ourselves at each position, is there the same branches, same chain, and same functional groups? In both cases, we start with the aldehyde group, which will be at the top of our Fisher projection because we ordered our Fisher projection with the aldehyde or ketone group as close to the top of the molecule as possible. We list the carbon atoms vertically, going down the chain here, and at each position along the way, we ask ourselves, are there the same branches and functional group? Here, where I've highlighted right here versus here is the same. Coming down here versus here is the same. Here's the same, here's the same, here's the same, here's the same, all the way down to the end. It's the same in terms of what is bonded there, because in each case there's an OH and an H, an OH and an H. What differs is how the OH and H are oriented between these two molecules. With that information in mind, we can go ahead then and rule out the possibility that the structures are constitutional isomers in this case, because they do not have different branches, they do not have a different chain, they do not have a different functional group. That is consistent amongst them. What differs is how the branches are oriented in three-dimensional space. In the case of the first chiral center here closest to the top, for example, the OH group is on the right for D-glucose, it's on the left for D-mannose, suggesting that the two structures are related as stereoisomers of some sort here. So to distinguish between diastereomer versus enantiomer, what we're going to do is look at each chiral center, ask ourselves whether the stereochemistry has inverted at that position. If it's inverted at every single position, then we will recognize that the two structures are enantiomers. If it's not inverted at every single position, then we will recognize the two are related as diastereomers instead. So taking a look here, we have our chiral center here versus here. That's our first chiral center as we come down the chain. OH group is on the right, versus OH group on the left, that means that that position has inverted. So I'm just going to label that as an inverted chiral center there. Coming to the next position in our chain here, that's here, start in blue versus here, that position has not inverted because the OH group is on the left here, and at that corresponding position in D-mannose, the OH is also on the left. So I'm going to go ahead and label this as not inverted. In other words, the RS configuration is the same at that particular position between D-glucose and D-mannose. Going on down the chain here to the next spot in line. At that next spot in line, what we find is we have a chiral center here versus here, and in both cases, the OH group here and here is on the right, and therefore we would classify this as a chiral center that is also not inverted, going from D-glucose to D-mannose. Then we come to the last chiral center. That's the chiral center that dictates whether the molecule is L or D in terms of how it rotates polarized light. Looking at the two structures, both of them have the OH group on the right, so we would describe that position as being not inverted. And it's no surprise that position is not inverted because in order for the structures to be referred to as D-glucose and D-mannose, that indicates that that last chiral carbon has to have the OH group on the right. By definition, that's what D refers to. So taking a look now at all of these chiral centers, what we see is that only one of them has inverted in going from D-glucose to D-mannose. As a result, the relationship between the two structures we would not describe as enantiomers, because enantiomers would refer to all the chiral centers being inverted in terms of who's left and who's right, but instead only one of them has changed, and therefore we would refer to the two structures being related as diastereomers. If any number of chiral centers have inverted, but not all of them, then the two structures are related as diastereomers. So diastereomers is the relationship between D-mannose and D-glucose, two of the very common monosaccharides. Let's try another example problem. In this example, we're asked, based on the structure of D-glucose, which we are given here, draw the structure of L-glucose. What we need to remember in order for this problem is that the D and L stereoisomers are enantiomers. It will always be the case that if one molecule rotates polarized light clockwise to a certain degree, then the enantiomer will rotate polarized light in an equal and opposite direction. And so keeping that in mind, D-glucose and L-glucose rotating light in equal and opposite directions means that they must be enantiomers, and we need to draw them as such. When we are drawing enantiomers, remember that all the chiral centers have inverted. So what we need to do is look at the structure of D-glucose, pick out each of the chiral centers, and remember to invert them in terms of, in the Fisher projection, whether the OH group is on the left or the right. So that means that we need to focus on these four positions that I put the light pink highlighter on, and we need to make sure that we have inverted who's on the left and who's on the right. The rest of the molecule in non-chiral centers is of no matter to us. So fill in the CHO group. We don't really have to be worried about what's the stereochemistry of that. CH2OH at the other end of the chain is not a chiral carbon either. So we could have put OH, CH2 if we wanted here. It doesn't matter since that's not a chiral carbon. What matters is at each of the chiral positions, which we represent with these crosses, we have to make sure that we invert the configuration at each and every one of those positions. I'm going to show that inversion in pink here to represent what we've done. So our OH group, which was on the right at this position, needs to be on the left here. The hydrogen then has to be on the right at that position. At the next spot, we have H on the right, so it needs to be on the left over here. So I'm going to put the H on the left and the OH on the right, therefore inverting the configuration at this chiral carbon that I'm highlighting from here to here. Same game, going all the way down the chain. OH group at this chiral carbon is on the right in D-glucose, so it needs to be on the left in L-glucose, hydrogen over here. And then at the very last chiral carbon of the chain, OH group was originally on the right. That's what makes it D-glucose. Now that OH group, to make the enantiomer, has to instead be on the left. And that's what causes this molecule, in fact, to be described as the L stereoisomer, is that the last OH group is on the left, whereas in the D form, it is on the right. So as we draw this, we've gone through and we've inverted every single chiral center down the chain. If you've done that correctly, a way to check your work is to imagine that you had placed a mirror here between the two structures. And if you're so inclined, you should be able to imagine in your mind's eye that the two structures are mirror images of one another. So mirror image here, because if you think of the OH group as the thumb of the molecule here, the thumb points to the right on this hand, it points to the left on the other hand. And same way all the way down the chain at each position, we've created the mirror image of the structure on the left in drawing the structure on the right. So now with this information in mind about the stereochemistry of sugar molecules, we should be able to apply this information toward drawing molecules that have a specific relationship to a starting structure, such as drawing L-glucose, once we know the structure of D-glucose. We should also be able to draw structures that are related rather than as enantiomers, instead as diastereomers or constitutional isomers, and we should also be able to look at two structures that you are given, and you should be able to specify based on those two structures you're given whether they're related as enantiomers, diastereomers, constitutional isomers, or none of the above. They're just totally, completely different molecules.